Okay, so I just want to talk, briefly about this idea of total internal reflection, and we can use these ideas to expand what we already know about optics, about light, the study of optics, and also what we know about the study of waves. So here's two things that you should just be able to hopefully really quickly answer in your head. Like if I say, what is the law of reflection to you, you should just be really quickly coming out with the law of reflection is, well, the angle of incidence is going to equal, the angle of reflection. I don't like how I wrote that. The angle of incidence is equal to the angle of reflection. Yeah, something really, 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 really easy like that. That's what we should be talking about when it comes to reflection. What happens when light travels from a high density to a low density? Well, it refracts, it changes in speed. So it changes in speed, and since it's going from somewhere of a really high density to somewhere of a really low density, it's going to speed up. The velocity is going to increase. These are ideas that should just come really intuitive and not be something we're struggling to find in ourselves. And if we're in that position where they're just really easy to access and make sense to us, awesome. We're in a great position where we can start talking about, more complicated things like TIR, total internal reflection. So here's a bunch of examples of total internal reflection actually being used. We've got things like fiber optic cables here. Now, fiber optic cables, they are over here. And fiber optic cables, well, they're these tiny, tiny, tiny cables of glass, about as thin as my hair, or your hair for that matter. And so they're really, really thin and all bundled together. They're glass, they're transparent, so they can have something reflect through them and reflect through them at the speed of light if we're using light. So we can have a signal travel through really, 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 really quickly. And we bundle loads of these together to get more and more signals. It's amazing. It's great. Um, you know, total internal reflection can be just used like chords like this, where we're lighting things up. These are making some really fancy lights that she's staring at. We can just see total internal reflection happening in this perspex blocks going along there. We've talked about sending signals here, but of course, receiving signals as well. Here we've got an endoscope, so we can put this down somebody's throat, and we can look at what's going on in there, and get that signal bounce back really quickly. Now, the advantage of using fiber optics is because we've got all these tiny glass fibers, which are the thickness of hair all put together. They have flexibility, much like hair does as well. So instead of just taking like a big rigid object and jamming it down someone's throat, which is horrible, or up the other end, which also isn't pleasant, yeah, or any of your other holes or gaps in your bodies, no thank you, yeah, instead of just sending something really hard and rigid down there, which would just be horrible, yeah, we can send something that is a bit more flexible, yeah, it's really flexible. So it's these really thin bits of glass, so they're flexible. And there's one hard bit of glass, that'd be horrible. It gets to the end, it would shatter and glass everywhere. Oh no, glass up any of the holes. No, no, thank you. No. So, total internal reflection. What we're going to say today is hopefully we can talk about what TIR is, talk about it briefly there, understand what critical angle is, understand how light travels across fiber optics under the influence of said critical angle, and give 3 uses of optical fibers. I just gave you a bunch. You know at least 3, you're in a good place. Okay, so this is what we said at the start. Reflection. Angle of incidence, yep, equals angle of reflection. Easy. Goes in, comes out, reflection. Wonderful. We know this. Let's stop talking about it. Refraction. Yeah, refraction. Light changes speed, or another wave, whatever we're dealing with, changes speed, and that can also result in a change of its direction. It wouldn't change direction if it was going just straight in like this, directly along the normal. But it would still change that speed. Speed, something that's always happening. It's common to refraction. The change of speed, always going on. Wow. That was strange. Okay, so why does it look like this? Because of refraction, right? You've got that light, that is bounced off that pencil, and because it's traveling through one medium and another medium, it changes speed, changes direction, and that changes the position, the apparent position of the image we're seeing. It looks like the pencil is bent, it's in a different place. Is it really? No, but the optics make it appear that way because of refraction, because of these different densities of materials that our wave is traveling through. Now, let's talk about something called the critical angle. We'll use these three diagrams here because I think they're wonderful for displaying the point. Here we go. Let's start with the start because that makes sense. Silly me. Let's use my highlighter because that makes sense. Okay, so if the angle of incidence is less that critical angle, most of the light passes through. Okay, so this is an example. Critical angle is just a property a material has. It's a property it has. And in this situation, it's less than the critical angle. Most of its intensity, maybe we're talking about, I don't know, 98%. This is black. 98% has refracted, and maybe 2% is reflected. Okay. That's scenario one. That's what we've been looking at so far. Yeah, we are getting some reflected. We're not getting reflection. We haven't been getting perfect refraction. We're getting some reflection and a weak reflection. And that's because it has been less than something called the critical angle. Facts we need to know. Now, this second situation here, if the angle of incidence is equal to the critical angle, most of the light travels along the surface, though quite a lot's reflected back. Yeah? Now, the third part is the bit that we're really interested in today. If the angle of incidence is greater than the critical angle, all of the light's reflected back. And we can see that starting to happen. The process of all this stuff happening in this other diagram up here. We can see as we're increasing and increasing that angle and finally getting to past the critical angle. Past the critical angle, we get this total reflection. And that's happening inside our object. So inside our glass, inside our perspex block, whatever. And so it is totally internally reflected. It's totally reflected because that reflection goes on and on and on and on and on. It's internal because it's inside, right? So we can end up just like completing this light path and showing what's going on. Well, it's totally reflected. So these angles should be the same. Angle of incidence equals angle of reflection. And this can just start to go on and on and totally internally reflect. Here's another example of that happening in the fiber optics. So we can see all these tiny cables, fibers joined together, and that gives them the ability to bend like this. And so this is really useful because, as we said, going down the throat or whatever you're doing, if you need to weave around some turns, it becomes a lot easier to do. Here we go. There's something this should have. This should have arrows. So here we can see you can put multiple signals here as long as they're not interfering with each other. But something really useful to have is something called cladding around the outside. Here we go. So like this cable here has cladding, rubber cladding on the outside. Now that is to protect the cable. But in the case of, well, it hasn't done protect it very well here if we look here. Oh dear, oh no. But that's very useful for protecting our cable. So we like to have cladding on things in general, yeah? But in this situation, it's especially useful because it stops the light leaking out. Yeah, it stops the signal from leaking out. Now imagine if we had loads and loads and loads, let's clump my hair together. Let's imagine we had loads and loads of these hairs are all sending signals through each other. We don't want them all interfering with each other, or interfering with the outside world, or the outside world interfering with them. So we put this rubber cladding on the outside, something that's also, going to be flexible to stop those fibers from touching, which might make them leak. Yeah, because let's think about it. If we've got loads of cables under the ground, I don't want your cable that's sending signals to you, and my cable that's sending signals to me to overlap and confuse our signals. That would be a bad, bad time. Uses data transmission, right? Data transmission, whether that is broadband, CD players, we're thinking about the past there. Compact discs still do have their place in some things, but broadband, fiber optic cables, really, 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 really useful. In the past, when I used to play, like Quake and like Doom and stuff like that online, and we didn't have fiber optics. We were just using, telephone lines, and if you're really lucky, maybe had an ASL line you'd put in, and that would be really, really slow because of the lag. Yeah, you'd go to like shoot someone, and by the time like you turn, they were now like there and stuff like that. It was horrible, but it was amazing because it's all we had. But broadband, the reason we're getting these really awesome signals now, and you can do all this crazy stuff and send like 4K video in like real time and things like that, is due to us having these fiber optic cables sending signals as light at 300 million meters per second. Boom, crazy, right? There we go. Oh, being signified by loads of these zeros and ones. Well, that's just nonsense, but okay. So, light displays. Yeah, you can have fiber optics making really fancy patterns and stuff like that, which are fun to look at because pretty things are nice. I like pretty things like that. Those things. Some of us might have had those in our room at one point. Endoscopes, that thing we were looking at before, the medical instrument to go down or go up. And there we go. There's a guy staring at his endoscope, and we can see it going down bodies and stuff like that. Typical application. Again, we're seeing it, and we're seeing it being totally internally reflected along sending the signal. And the arrows, really important to show which way it's going. Okay, so there we go. As we said, using communication, use total internal reflection. There we go. This one's showing how it can be bent and still send the signal along. Doesn't matter. It can just keep on going. Yeah, which is wonderful. It's not restricted by being a rigid, cable or anything like that. That was a whirlwind tour. You might need to watch that again because I like talked very fast. Pick one of them. Yeah, I said you need to know three. But just pick one as a focus exercise to try and embed this information. Pick one of the uses, tell the story of how it works, what's the science of how it works, why was fiber optics the good choice to send this signal, and draw it out. And if you can do all of those things, you have a really nice rounded package of what goes in the TIR. I promise you that. Wonderful. Look at these pretty pictures.